for those our first time take my class, right? On the website. And I usually give you a lot of examples for the homework assignment during the lecture. And the lecture is recorded and notes are submitted as a PDF to the website. And so when you are doing the homework, you can watch the video and look at the notes, right? And so you feel comfortable, you are not feeling alone because somebody is always talking to you on the website and in the thick Chinese accent, and and you feel happy about that. So you sum up, right? In the end of the semester, you just sum up. That's what you usually do, right? Let's see. Here's a signal. If you're starting from here, it's a sine wave. If you start from here, what is this? Cosine, right? And in the signal system, we treat the cosine signal as an in-phase signal. Doesn't matter which one you want to call it in phase. So this is the in-phase signal. That's something you want to compare with. So that's the in-phase signal. So a sine wave will be something has a 90-degree phase shift. And also another name for that one is a quadrature signal. Quadrature signal. And when you are adding these two signals together, you can generate another sine wave signal. Remember on Wednesday, where did we demonstrate that? LT spice, did you remember? We saw another sine wave, the third sine wave, by just simply adding these two signals. And these two signals has a how many degree phase shift? 90-degree phase shift. So they are quadrature signals, and you add them together, you get a third signal, and that's a sine wave as well. And you can simply changing what? By changing the third sine wave's phase and amplitude. Okay, that's a question. Okay, you're not like no, that's a question, right? So by doing what? You can simply change the third sine wave's phase and amplitude. By simply changing the amplitude of either one or both of them, doesn't matter. So which means by simply changing the amplitude of these two signals, which has a 90-degree phase shift, these two signals, just by simply changing these two signals' amplitude, so the generated signal, the third signal, the phase and amplitude of that signal can be changed, right? And this behavior is dominated by equation. I can write it down right now. So I wrote it on the paper on Wednesday, but I can do it again. But so the idea is I can just simply change the amplitude of the input. So I can get an output which has a specific phase shift and also an amplitude change. Why is this important? When you are trying to generate different types of signals with a different phase, any other technologies or any other techniques you can do, you can make it happen. Why is this super simple? I'm just trying to attenuate, or I mean, I don't know if that's practical or something, but just think about the model. It just have a little potentiometer, so you can change the resistance of the circuit. So you're changing the amplitudes easily, and you are generating a third signal with a different phase or different amplitude easily, just by tuning the amplitude. You don't even need to tune the phase of the input, but the phase of the output will be changed by changing the amplitude. Why is that? Let's look at the equation. AI, remember what is AI? Artificial intelligence. What is AI? The amplitude of the in-phase signal, right? Which is cosine, right? 2 pi f t. So the cosine function is a function of t. So AI times cosine 2 pi f t plus AQ sine. So Q is a quadrature signal, sine wave, 90-degree phase shift. So these things are not. I don't want to say that. I was trying to say they won't be on the exam. If I say that, you'll just let's relax. So these things are just trying to help you to understand what's more important after this. I mean, since we are going to use the equation automatically, we don't need to think about all these things later on. But if you understand that, that'll be easier. If you don't understand something, but you memorize it and just trying to use it in the future, you'll forget it after the final exam, like what you have forgot in circuit 1. Right? Since you hate it and you don't like it, you just don't want to work on that anymore. That's why you forget everything. If you understand that, it's intuitive, it makes sense, so you can memorize this for a longer time. Can be like 2 weeks longer after the final exam. It's helpful. All right. Yeah, 2 pi f AQ sine 2 pi f t. So you just changed amplitude, right? You're not changing anything else. Are you adding a phase shift in the equation? No, you are not. You're not adding anything inside the cosine or sine function. So you are not changing the phase. There's nothing involved to change the time. So you're only changing the amplitude. AI, AQ, doesn't matter, you just change it. So what's the final result? That's the final amplitude, right? So when you are looking at LT-SPICE, you can verify that by yourself on your side if you like. Okay, so you have 2 signals and you know AI and AQ, you change it and you look at the final result, the third sine wave, the amplitude will be exactly this number. You can verify this in LT-SPICE. And this is amplitude. What's the phase? I couldn't even remember that. Cosine, right? It's cosine 2 pi f t plus. Whenever you have a plus or minus inside the cosine sine function or sine function, which means there is a phase shift plus what? Plus tangent AQ over AI. So this equation, that's a magic of maths, right? Whatever I just talked just now for how long? Like it's been 10 minutes at the beginning of the class. So all these 10 minutes, what I just talked about, can be totally covered by this simple equation. Is that making sense? Are you changing the phase? No, you are not. Sine wave, cosine wave, 90-degree phase shift. In phase, out of phase. 90-degree out of phase. You're only changing A and AQ. See? You got a phase shift. Depends on AQ and AI, the ratio between these 2 numbers. So that's why you are looking at the third sine wave in LT-SPICE. When you are changing these 2 numbers, you are seeing a changing at phase and also amplitude, right? Okay. So the idea is, I have circuit, and I want to send a signal to somewhere else. And what I want to do is, I just want to change the amplitude, and then I'm going to change the amplitude and phase of the output signal. Keep in mind, you always think about the input and output in the system when you are working in anywhere, academia, in industry, for engineering company, for construction company, electrical, software, hardware, anywhere. As engineer, right? So you are caring about input and output. So what's the input? Variations of amplitude. Can you do it? Yes. Change the potential meter, right? What's the output? That's the product. I really need signals with different phase and different amplitude, right? We're done. We just need to change the amplitude so we can change both amplitude and phase of the output. We're done. So that's the input and output of the signal. And that's the only thing we care about, right? So that's a quadrature signal. Why it makes sense? When I'm saying cosine plus j, I don't have a variable here. Let's cosine k plus j sine k equals to jk, right? We derived it last time on Wednesday, the Taylor series. Euler formula, right? So why this is being used for signals? Why does this make sense? Why do we want to do that? This makes sense, right? Remember, LT-spice demonstrated already. Just changing the amplitude, we can change both phase and amplitude. Makes sense, easy. But why does this make sense? Exponential equation, why is this a sine wave? Imaginary, but still not intuitive, right? How can you convince yourself? How can you convince yourself you understand? Why do we use E? Why do we use J? I just never convinced myself, in the past 20 years, until most recently, Since I don't need to care about that, I just need to pass exam, as most of the students and the professors know the students only care about that, right? So now think about that. Why does that make sense? Phasor, yes, phasor, close, it's getting close. Yes. And also, keep in mind, I just mentioned one super important thing you want to keep in mind for entire life. You are working with engineering field, okay, any kind of engineering. You only care about the input and output, right? You don't actually care about the details. This is not a sine wave, I can tell you. It's totally not how it can be a sine wave. Even J itself is not making sense. What is J? Square root of -1. It's not making sense at all to the real life. It's not. But however, we can use it as an engineering tool. It's frozen. To care about our input and output. As long as we got our input, we process with our model, we got a specific output, we're done. We don't care about whatever is inside the system. Can be used as a calculation tool. So for here, you actually add them together. You add them together numerically, and you get this result in a real number domain phase, right? So the real number domain makes sense. This works, makes sense. It works in LT-spice, working everywhere in math. But this doesn't work. You cannot add a real number to an imaginary number, right? Can you? You cannot. It just never work. But you still put it in here. Why do you still want to use it? Because J can separate the real domain and the imaginary domain. And when you are doing any numerical operations, you only add up the real number part and the imaginary part. You never add your real number to the imaginary number. So this is not addition operation. You just literally put them together. You just think about, I just lay out two numbers, a real number and the imaginary number, which has a sign in the front. You know what I mean? You're not adding them together at all. You just use a J to separate the two parameters, which one, the real number domain, another one is the imaginary number domain. And finally, so here's the result. And why we can use this one to represent signals. Whenever we're telling about this thing, this is the phasor, right? Look at the coordinate. Why is this a phasor? Come back to the unit circle. Okay, unit circle. The R, the radius here is 1, right? If I draw a bar, so the bar is the phasor. So why the bar is the phasor? The bar is the bar. The bar is the bar in the circle. Why the bar is a sine wave? Remember? Why the bar is a sine wave? Because the bar rotates. And we can use the rotating behavior to represent what kind of information in the sine wave. What we care about. Amplitude and phase. That's only two parameters we care about, right? As long as this bar, we don't, it's fine. I know you are a bar. You don't look at sine wave. It's not pretty like sine wave. It's fine. As long as you carries information, the information of a sine wave, I can use you, right? As long as the bar carries both amplitude and phase information in there, that's all the information I need to represent the sine wave. I'm done. Make sense? The phasor is a bar in the circle. It's not a sound wave, but however, it carries both the phase and amplitude information. You know that? Phase. Yes, the length of the bar is the amplitude. Only when the bar, as you see, when the bar rotates to here, it's a maximum amplitude. So when you are looking at sound wave, so when the bar is here, so starting, remember last time on Wednesday we drew that. So when it's rotating, you get a sound wave projected to this coordinate. So you get a sound wave. This is not a sound wave actually, right? But we can use the information in the phasor to represent the sound wave. That's it. We don't care about anything else. We just need the amplitude and phase, and we're done. We just use this information to be used in your electrical system. Okay. So that's a phasor. Why? That's the imaginary domain. That's a real number domain. That's whatever j, that's whatever here. This is here, the x-axis. So it looks like, if I don't draw the circle, it looks like a point, and you can project to the two axes, right? So what's the length here? If I draw a bar, and this is k, what's the length here? If the length of the bar is 1, cosine k, what's the length here? Sine k. But we really need both of them. So both of the two information here, they are required to form this kind of phasor, which is this guy, which is the sound wave. We need both of these two information to represent the sound wave. Is that making sense? Even it's not 100%, but what about 90, 80%? You are trying to getting to that point. Is that making any sense? Is that making any sense? Yeah. You're not cheating yourself, right? When you draw a bar in the circle, it's a bar. It's not a sound wave. You can use that information in the bar to represent the sound wave. Okay? The bar is a phasor, carries the information. Okay. And now, because we need this and this, the real part and imaginary part, to form this phasor, which is a sound wave. So that's why, and they cannot be added together since they have a phase shift. They're not in the same domain. You cannot directly add them together. You have to use something to separate them, which is J. Okay, and I separate them when I'm adding two signals together. For example, 1 plus 2J plus 2 plus 3J. What's the result? 3 plus 5J. See, that's why we need a J there. If you don't have a J, then it's going to be 3, it's going to be 5. So J is separating the imaginary part and the real part. So this is the phasor, right? Is this also a phasor? Yes, it is. Why? There's no cosine sign. Why is the phasor as well? Well, let's give you some examples. I have a few examples. So now let's start from an easy one. 1 plus 2J. Still use the same one. So that's a phasor, right? So compared to this guy, what's the difference? It has a different what? Different amplitude. So what's the amplitude here? How can I calculate amplitude? What's the amplitude of this phasor? 1. And 1 means it's inside a unit circle. What's the amplitude here? Apparently it's not 1. It's just a longer bar. Just a longer bar. And whatever is longer or shorter, as long as it is a bar, you rotate it, you get a circle. You get a circle, you project to another coordinate, you get a sine wave, right? So this is the sine wave. So this is it. This is the sine wave. Is this the sine wave? Yes, it is. Is this a sine wave? It's just too bad. I mean, it's just a dot here. You have to have some dimension to draw something, right? You have to have at least a 1D. What is 1D? Yeah, but I mean, what is one dimension? Point is 0, right?
But how do we know what angle to draw at different times?
Oh yeah, so angle. So 2 and so you got 2 here on X, on the Y, 2 here, right? And 1 here. So actually the bar is like this actually. So do you know what's the angle here? What's the angle? Tangent, inverse tangent 2/1. So that's the phase. That's amplitude. And we only care about these 2 parameters. And that's it. So why that's a phase? I mean, how can you reflect this kind of phase in the sound wave? So when you draw a bar here, which means if you want to say this is a phasor to other people, you want to tell people that's time 0. That's when the bars start rotating. So now let's look at that. Time 0, that's time domain for the sound wave, right? T, amplitude for the sound wave. And that's time 0. How can you draw it? How can you draw the sound wave? Project it. At which time point? At which time point? This is which time point? Time 0. Boom, 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 boom. Right? And then there is another time point. I actually don't know what is that, but it's going to be something here. And then the bar will start rotating until reach here, probably. Apparently, it's higher than this point, right? So we're getting a peak. And then it's going to start dropping and then start coming back. Now let's draw the sound wave. Is that in phase? No, it's not. That's a sound wave. Compared to the time 0 coordinate, it's not in phase. Is that leading or lagging? It's leading. Why is leading? It's on the left side of the time 0. So now you can tell if the signal is leading or lagging. By how much? Can you tell leading how much? Which is the phase shift. Leading by this kind of angle, right? So this part is theta. How can I convert theta into time? This is time. It's not making sense. You put a theta here. You have to know the frequency first, right? How? How do you know this angle here? No, so you know the angle. How do you know the time? Because you are talking about time delay. Phase shift, the unit of phase shift is angle. The unit of time delay is second, right? And now you are talking about something in the time domain, which means you are going to translate this theta into time. How? So what does that mean? How many share does this angle have in 2 pi, which is overall angle? That's a share, right? It's a percentage. So this little angle is about 10% in 2 pi in the entire angle. How long it takes to rotate the entire angle? How long it takes to rotate the bar across 2 pi? That's angular speed, velocity. I mean how long it takes to rotate your bar through the entire circle, which is the period, right? What is the period of the sound wave? Yep, but can I just say t? What is this? What time? Delta t. This angle represents delta t, or time delay. If the time delay, if the signal is leading, the time delay will be negative. So you are delaying a negative number, which means you are leading. So sorry, I mean, I just look at your face, are just being puzzled, and that making sense. Even a little bit. I mean, it's recorded, so just watch it again and again, and during the lunch when you're driving, and just try to reinforce the knowledge, right? Oh my goodness. Thinking about Phasor, it's gonna take a week. Thinking about Phasors. Any questions, just ask. Don't afraid to ask questions since everybody is getting confused. So don't be shy to ask anything. So that's a time delay actually. The reason is that's a share because the t is a period, which is the same as 2 pi, which is the angle. So when whatever the theta, whatever the percentage of the theta taking in the 2 pi, in the entire angle, it's going to be the same ratio, the same share, amount of share it's going to take in the entire time of the cycle or the period. So that's why that's a time delay, because theta is the phase shift. That's why times t over pi and times t will be the time delay. If it's leading, you still have a time delay, but it's a negative time delay. It's making more sense when we are doing calculations. But now you know that if you have something like that, it's a sound wave and carries information. What are the information? Amplitude and phase. And if you know that, you know everything. You can draw it, and you know what's the time delay compared to the in-phase signal, and you know the amplitude. I started from here. I don't know anything else. And now I get that. You get that? What about this? It's a phasor, right? So what's this is a really nice signal. Why is that? Because it's what? In phase. Is it in phase? 1 and 0. There's no amplitude on the imaginary plane, but you have 1 on the real plane. So it's a bar laying down here on the x-axis, right? And what's the signal? Oh, sound wave. I'm sorry, it's not in phase. It's 90-degree phase shift. Consider as 90 degrees, so it's a sound wave. Starting from time 0 here is a bar, which is there's no amplitude over there, right? Starting from 0 amplitude at time 0. Sound wave. Yeah, so tangent, which is 0. 0 phase shift, right? So that's the theta. Is that 0? Tangent 0, inverse tangent 0 is 0. Since because there are phase shift involved in the signals, right? So that's why you have to tell how much is leading or lagging, so which is the phase shift. Because if you only have amplitude, it cannot carry too much information. There are so many other things are carrying different information, like phase shift, amplitude, and that's 2 of them, and probably that's every of them. And sound wave there are only 2 kind of information. One is phase shift, one is amplitude, and we care about time delay a lot in different places. For example, one place is industrial automation, and you care about the time delay, because so think about that. You are having a shower and you're turning the knob, and it takes a huge amount of delay to change the water temperature, and you change it to hot, but it's still cold, and you think it's not hot enough, you just make it hotter and hotter, but finally you got a 100 Celsius degree water, boiling water, because there's a time delay for the water for the pipe to get response to adjust the water temperature. So they have to merge more hot temperature water to the cold water to make it warmer or something, right? But the thing is, it takes time, so you got a huge amount of delay. But your brain can respond to temperature really quick, way faster. So you are sampling the data faster than the system itself. So the result is, you change it to here, you feel it's too hot, it takes time to respond for the system, and after a while, it's still hot. The hot water just comes over, and it becomes super hot, and you are just trying to make it cold. You just change it to the far left side, but still not cold enough because the system is slow, right? So in that case, you feel you need to make it hotter. Then you change it to here again. So what's happening over there? What's happening? What's happening? It's oscillating. It's a huge problem. You have to compare the time delay to your sampling rate of the system. How do you know your system is sampling or not? Or how do you make your system sample data, analog data? Use an A to D converter, analog to digital converter. And you can buy a little chip which can do the A to D conversion, or Arduino has a 10-bit ADC inside the chip, so you can directly convert a temperature analog data into digital signal. If you need a more higher resolution AD converter, you can buy a better one from Microchip. All the MCP, I forget the versions, but all the MCP series can reach up to like 14-bit resolution. And you don't know what are bits, right? Take logic in the summer. You understand what are bits, what are byte, what are giga, mega, all these things. Yes. Yeah. So you can change the amplitude, or you can change the frequency. It's called modulation, right? So you are changing frequency and amplitude to carry different information for the signal. Great. Yeah.
So on Phasor, how do you know when it's leading or lagging? Based on
compared to the time zero.
Quadrant it's in your picture?
Based on quadrant you have to set up an in-phase signal. So all the signals are leading or lagging, they are relative. We don't care, there's no absolute signal. You have to set up a reference first, and then you compare to that reference. So usually we compare with a cosine. So actually this signal is not actually in phase. We draw a cosine signal, and the sine wave will start from here. Yeah. So I give you so in the future examples in the homework or exam anywhere you can see. So there will be an input signal with a specific phase, right? And you don't worry about what that phase is. And after you inject your input into a system, you get output. And you can find out what's the phase and amplitude of output by calculating that, right? And then compare the output to the input, you get a phase shift. So you can tell how much delay the system is generating to your output compared to the input. You don't care about your output signal compared to some signal in China. You don't care. You just care about the input being injected into your system and how much delay is being generated by that system. So you know you can characterize your system, so how much delay is generating by the system, okay?
Can you give an example of one that's lagging?
Yeah. 1, -2. Where's the phasor? Lagging. If you don't want to just draw everything on the paper, make it more graphical, what you can do. Actually, we never care about this at all in the future. We just look at this. Good enough. What's the theta? It's going to be a negative angle if you calculate it. Just use the online calculator. Let me show you how to do it. Inverse tan calculator. Now let's take a look. This. All right, let's put -2 there and see what's the angle. -63 degrees on the paper here. What's this angle? It not depends. It's like exactly. Okay, we don't do that. I mean, let's just make it work. All right, so it just follow. Okay, just do this. You got that. You don't rotate it backwards. It's giving yourself more trouble. You use this kind of model to help yourself, right? So that making sense? If you have this, you got this. How you got that? You got this. You use this one to get this. Okay, so you'll see a lot of examples in the homework asking you to calculate what's the time delay what's the time delay of the output compared to the input. So you need two signals, right? That's V in, V out. Now let me know. Now let's change it. It's 1 minus J. 1 minus J means 1 minus 1J, right? So the imaginary plane has a 1 as amplitude. Now let me know. What is the attenuation? So the attenuation is V out over V in. Absolute value of that ratio. Can you calculate that? Get amplitude here first. What is that? 1 plus 1 square plus minus 1 square root. That's VO's amplitude. What about V in's amplitude? Yep. What's attenuation? Okay. And then you can do a calculation. What is that? So this is 1.4. This? I can remember. One was in high school. One was high school. I was like 16 years old.
What, 5 years ago?
No, just last year. I'm 18 years old. And I have 2 kids. Wow. So you can calculate this, right? So it's going to be like something like 60%. So we got 60% attenuation. So let's just say this is attenuation. So that's VO over VI in terms of amplitude. That's easy, right? So forget about everything I told you on Wednesday and Monday. So now we just start just working with all these phasors. We don't care about whatever I told you, the quadrature signals and all these things. This is helping you to understand where this comes from, right? And now I got that concept, and now we start working with applications. Sound wave, sound wave, sound wave, sound wave, all sound waves. And that's the amplitude ratio. That's attenuation. Output over input in terms of amplitude. What's the phase shift? The angle of VO minus the angle of VI. Is that making sense? I don't care about what are the exact phases they are. We just care about what's the difference between these two phases. These two phases. So we get a phase shift. So we get a time delay. We don't care about where VI, Vin get started. We just care about how long it takes or what's the time delay between VI and VO. How can we get these two numbers? What's the angle? What's the angle of VO? No. Yeah. What's the angle of VI? Can you get a phase shift? Yes, you can. What is that? Calculator. Yeah. So that -2, oh, this is +2, right? So we need a -1 here. Calculate. I think it's -54, 45. Minus what? Tangent 2. Calculate. Wait. Oh yeah. Sorry. Yeah, 63.4. Let's come back. What's phase shift? That's a lot of phase shift. Yeah. It's minus 108.4 degree. Okay. That's a phase shift. How can you draw the signal qualitatively on the paper? How can you draw the VI and the VO? I'm going to ask you to draw that. So V in, just draw it. That's V in. What's V out? 60%. If this is 1, what is this? What's the amplitude of that guy? 0.6. And now you know the peak. What's the time delay? It's so right now here is a negative phase difference. It's different from the single phase, right? For the single phase, you have a negative number, then that's that's a specific, that's a angle just for that signal. But now you have a difference. So the difference means it's a negative difference. So it's going to be a time delay. You get that? Why is that? Because you can verify that. So this guy is a negative number, right? So negative number means it's lagging compared to 0. And this is a positive number, so it's leading. And you are using a lagging signal minus a leading signal. It has to be a lagging signal. So whenever you see a negative number here, it's going to be a lagging signal. So which means it's a 108.4 degree. It's going to be something. So that's 180, right? That's 90. So this is probably something around 100 degree. What's the question?
Yeah, based on how you define the time delay,
Mm-hmm.
the angle of the output
Mm-hmm.
minus the angle of the input.
Yeah.
Is it ever going to be a positive number? It makes sense that it's always a negative number because your V out is going to have some time delay, so it's lagging, right?
Yeah.
So, but is there ever an example where it's leading?
Yeah, so it depends on how you define that. Usually when it's over 180 degree, they are treating that one as a leading signal because it's lagging too much, and because the signals are exactly the same. When you are treating it as a lagging, but it's more than 180, it's probably easier to just directly use it as a leading signal. That's what I'm thinking. But we probably don't have that much of time delay in our examples. But that's a good question though.
Like the input laps the output and you just start off and then.
Yeah, so sometimes, so for example, is that making sense? Like you are lagging like 1000 D-ray, right? It's more than one cycle, right? So it's coming back to the cycle. And you actually, by that time, you actually couldn't tell if it's leading or lagging, because the signal is just like so close to each other, and you'll probably just treat it as lagging. It's like super tiny signal. So there might be a definition for the upper limit for how much signal you can lag or how you can lead. Probably it's 180. So whatever smaller than that, you can treat it as leading or lagging. Whenever it's more than that, it's just reverse lay. So for this one, it's 108 degrees. No, it's so that's V in, right? And your VL is lagging because of time delay. So that's why it's over here. And also the amplitude is 60%. So when you are drawing that, you want to draw it in that way. So I'm going to just ask you to draw it qualitatively. So when you are point here is whatever you calculate here is probably not 60%, probably can be something I just roughly calculated. And whatever you get the number is over here, you just label that over here. It doesn't have to be exactly, you don't need a ruler, right, to calculate. It's just like roughly draw that signal and tell me what the output amplitude is, and you point to the time delay point and tell me what's the time delay here. Just label that on the paper when I'm doing the homework. Making sense? You have such homework in your, which is due Wednesday. Okay, it's not due on Monday because I know if you have problems, you have questions, you still have an opportunity to ask me on Monday, also during the lab on Tuesday. Okay, you get opportunity to ask that. That's why I don't make it due on Monday. Usually I make it due on Wednesday. And I think that we still have 4 minutes. Let's look at the homework assignments. What they look like.
Will there be from now on? Nothing, no homework doing with these.
Nope. Draw the unit circle in the XY plane and the corresponding sound wave in the single sound angle plane. Easy. Derive the impedance of the cap and inductor when the input signal is E, J, omega t. So it can be a voltage signal for the capacitor, and it's going to be a current signal for the inductor, and I have exactly the solution on the nodes. Okay? What are the amplitude and the phase shift of the following sound waves? Compared to the sound wave, probably, because you know what I mean? So what is 5? What's the phase shift of 5? 0. It's a bar on the x-axis, 0 phase shift. And what's the amplitude? 5. Because 5 squared plus 0 squared square root, still 5. What's this one? What's the amplitude? What's the phase shift? I mean, compared to sine wave, not cosine. Okay, compared to the sine wave, 90 degree, and the phase and the amplitude is 5. What about this? 45 and square root 2. What is this? 90 and 1. What about this? Square root of 13 and inverse tangent 3/2. Got that? Next, phase shift compares output to the input. Leading or lagging? Can't tell that. So when you use the phase of the V out minus the phase of the V in, if you get a negative number, is that lagging or leading? Lagging. So the first one is pretty standard. Okay, what about the second one? 0. What is that? 0 seems like somebody shut off the power. Yeah, that's not a good example. Just, you know, say something, you know, I mean, it's, I forgot, why did I make this? All right, there's nothing. Anyway, what about this? Yeah, ignore that. Okay, just do the first one. That's it? That's all the homework? 1.1 to 1.4? Oh my goodness, so simple. So happy for you guys. Have a good weekend. Right.